was in my other class?
You're coming back.
I think you did last time.
I did last time, okay.
I remember you taking roll first.
Okay, good.
Everyone
I'm
was
going to
here.
try to remember this time, too.
Everyone counted.
Everyone account to
Everyone
4.
counted for.
So we've got a couple more examples of surface area. And we are doing surface area of surfaces that are found by rotating a curve around an axis. And what is your name? Welcome to the class. You're so soft and fluffy. So all of these surface area ones are just for surfaces of revolution, which makes it a little bit easier. So our general procedure is that we are approximating with frustums, with tiny little cone bases. Right? If you have a cone, you chop off the cap, that thing is a frustum. And so that's kind of what we're thinking of. So that's what our generic formula is representing here. This formula is representing a circumference right there. And if you take a circumference and then you add a little thickness to it, it becomes a frustum. And that's what the ds is. The ds is representing a little slant to the circumference. So that builds a frustum of a cone. So that's what's happening here. And the way, let's look at the previous slide for a second. So the formula we used here, we are rotating around the x-axis. So we have a function of x, and we are going to be doing y prime, and we're going to square y prime. When we're going around x-axis, we have functions of x, so we have to find y prime. Let's look at this next one. They kind of throw us for a little bit of a loop. They give us a function of x, but notice that they're saying, let's go around the y-axis. So our axis of rotation is over there. The general rule of thumb that makes things as easy as possible with surface area is that if you rotate around y, use functions of y, and if you rotate around x, use functions of x. So they've commingled it here. They say go around y, but they've given us a function of x. When we are going around y and we look this direction for our, for our representative frustum that's going to come around, this is an x distance, right? That's horizontal, yet they've given us the function presented as something measuring vertical distance. So we're going to want to convert that to x equals a function of y. That's going to be the easiest way to do it. So if I multiply both sides by 4, we end up with this, and then x is going to be plus or minus 2 times the square root of y. And I need to know whether to choose the positive or the negative. We're going to choose the positive. If we think about this graph here is a parabola. This parabola continues through the origin and back up over here. So the parabola is symmetric. It's got a positive half and a negative half. So this piece of the parabola is on the positive side. So we are going to choose the positive root. So that is that curve. We've now written it as an x value, so it's measuring distance from the y-axis, whereas this function is measuring distance from the x-axis. So that's what we want. We want to be measuring from the y-axis over. So that does what we want it to do. So there's the curve that we are analyzing. Now our formula says 2 pi r, which is right here. So this is the radius right there. That's r right there, which is an x, so that you could call that x if you wanted, but we need to rewrite it in terms of y because we're going to have a dy. So if we're going around the y-axis, we have dy. If we're going around the x-axis, we have dx. Okay, so we now need derivative. So the derivative here, the power on y is 1/2. The 1/2 comes down and cancels with the 2. 1/2 times 2 is 1. But then it will be y to the negative 1/2. And then we square it, because it's got to go in there, x prime squared. Dx dy is x prime. So there we have x written as a function of y, and now we have x prime written as a function of y. We square it, it's going to go in there. So we can plug everything in now. So surface area is going to be 2 pi, that factors to the front. This x, or this radius, that's the function written as an x value. There's what x is, 2 times y, 2 times the square root of y. So there's the x. And then we have the square root for the ds, and that's 1 plus y, 1 plus x prime squared. So 1 plus x prime squared. And that is our setup. We're going from 1 to 4. Okay, so is there any piece there that you aren't sure where it came from? So it's a little more complicated in this case because they mixed us, right? They gave us a function of x and said we were going to go around y. If we're going to go around y, we want functions of y. If we're going to go around x, we want functions of x. Now, when you have a pair of square roots, last time we saw that it's very pretty easy to combine them. You take what's inside of the first one and you match it with what's inside of the second one. You combine them.
Does the rule of like, if they want us to go around the y and they need it in terms of y, does that apply also to like washer method, this method?
With the washer and the disk method, we're always thinking of the element relative to the axis. So if we have a vertical element, we know we're going to integrate with respect to x. It's going to be a dx. And so then everything has to be in terms of x. Or you can say it's a vertical distance, so you write everything as a y value. Writing something as a y value means writing it in terms of x. And if you have a horizontal element, you're writing everything the other way in terms of y. So this is slightly different because it's not quite as obvious, but you can think the same way. If you have a horizontal element, this is measuring distance horizontally, so you should have x values on each side. Right? If you're trying to measure a horizontal distance, it's going to be x minus x. And if this function was given to us as a y value, we would want to rewrite it as an x value. So you can use the same logic. It's just not as obvious because we're not dealing with a washer or a shell is very visual. A frustum is a little bit more abstract. So you should be envisioning a circumference coming around here, and we need that horizontal distance, which means write it as x equals. So then we combine our 2 square roots, so the inside of the left root is distributed to the inside of the right root. So y times 1, y times 1 over y. 1 over y times y is 1. And that's a pretty easy integral because inside is just linear. So linear makes you say, okay, we could do it with RCR. What's the derivative of that function inside the square root?
Just 1.
Just 1. So it's actually, we're not even going to see the RCR because we're going to divide by 1. So if that coefficient was not 1, then we would have a more obvious division. So we are going to have y plus 1. So right now it's raised to the half power, so it's going to go to the 3/2 power and divide by 3/2. And then the RCR part, if that had a coefficient other than 1, we'd put it under here or put it out in front or whatever. So that division by 1 is for the RCR. I was going to do it in red just to match RCR because that's just a 1. So if the coefficient of that y was a 3, we'd divide by 3. And then our limits of integration 1 to 4. The coefficients can combine to 8 pi over 3. Plugging in the 4, we get 5 to the 3/2, which we've been writing this way as a simplified form of 5 to the 3/2. And then we plug in 1. 1 plus 1 is 2. 2 to the 3/2, which we would typically write in that simplified form. That will be the surface area. Any piece there you're not sure about? All right, let's do another one.
Wait, I have a question.
Oh!
What would be like an example of a non-linear?
So it's nonlinear if what was in here was y squared plus 1, if what was in there was sine of y. So if it's not in mx plus b form, then it's not linear. So the only time we can use RCR is if it literally is like a constant times x plus a constant, or in this case, constant times y plus a
So
constant.
what would you do? Like
Then you have to use a different technique.
Okay.
So then we might use regular substitution or other techniques that we're about to learn. Integration by parts, integration by partial fractions, trigonometric substitution. We're going to learn a ton of techniques. Yeah, it's going to get real. It's going to be so. All right. So with this one, they didn't commingle anything. Everything is straightforward. They give us a function of y, and we're rotating around the y-axis. Right, so that's all good. That all lines up. So when they say go around the y-axis, we're thinking, okay, well, horizontal element, that means the function has to be written as an x value, and it is. So here we don't have to do any converting. So we look at our formula. We know that this ds piece, that's arc length. So we have to take the function, find its derivative, square it, add 1, take the square root for the ds. And the r part is just the function. So let's go ahead and do the derivative piece first, since we know we need it. So this will be 1/2. We don't change the base. We subtract 1 from the exponent. And then we apply the chain rule, which says multiply by the derivative of the base. So let's simplify this before we square it, because what I notice is that this 2 right here, we can cancel that with this. And then this is a square root in the denominator. So we would write this as 6 minus y divided by the square root of 12y minus y squared. So that's x prime simplified. Then we're going to square it and add 1. Let's just focus on the squaring part. So squaring the numerator, we'll just write it as 6 minus y squared for a moment. Now we can build the surface area formula. So capital S, 2 pi r, so 2 pi factors to the front. We are told the limits of integration are 2 and 10. R, right there, the radius, that's just the function. That's measuring the distance to the y-axis, to the axis of rotation. So there's r, 2 pi r. And now ds is the square root of 1 plus x prime squared. So 1 plus, here's our x prime squared. So we're going to FOIL out the numerator, so that will be 36 minus 12y plus y squared. All that's divided by 12y minus y squared dy. Okay. Similar to what we've seen on the last couple slides, we've got a square root and a square root. To combine 2 square roots, we take the inside of the left one and distribute it to the inside of the right one. So this whole quantity in here, that just gets distributed. That whole quantity gets multiplied by each of these 2 fractions. And once again, we notice this kind of common pattern that we have a denominator that's going to cancel. So this will be the square root of, here's 12y minus y squared times 1. So that's multiplied by the first part of the second square root. And then when we multiply it by the second part, it cancels with the denominator, so we end up with just the numerator. And then we see that we have some common terms here that we can cancel. 12y minus 12y. Negative y squared plus y squared. So we end up with square root of 36. 6. 6 times 2 is 12, so we're going to pull that to the front. And when we do that, we are left with integral of dy from 2 to 10. And what does that equal? Integral from 2 to 10 of dy? 8. Very good. 12 pi times 8. So that's the length of the interval. When we integrate a differential, the answer is the length of the interval. Upper minus lower. Yeah?
Going back to the last problem, the one before this one.
Mm-hmm.
So say if they say they wanted in terms of, the last one they wanted in terms of, what was it, x?
So if we are going around y, the distance to the y-axis is an x value, so the function has to be written as an x value,
Yeah, but my
which it
question-
is. So on the prior one, they say go around y, but they didn't give us the function written as an x value.
Yeah, but they say how they give you 2 and 4 for the bounds.
Yes.
Do you have to convert those?
Yeah, gotcha. Good question. Okay, so the limits here are 1 and 4 because those are the corresponding y values.
Oh, okay.
Right, when we're integrating with respect to y, those have to be y values. So how do you get the y values from the x values? Well, if you plug in the x value here of 2, when x is 2, 4 divided by 4 is 1 for the corresponding y value. And then when x is 4, plug it in there. 16 divided by 4 is 4, so when x is 4, y is also 4.
Okay.
Yeah, good question. So that's why we have, yeah, so those are coming from the y-axis.
That makes sense.
Yeah, good question. All right. So last surface area one is kind of a light application. We're just finding the surface area of this arc that's rotating around the x-axis, but they guise it in the form of an application. They talk about volume of paint, and we want to paint this surface, and the paint's supposed to be 1.5 millimeters thick. So all we have to do is find surface area and then multiply by the thickness of the paint. And if we change the thickness of the paint to meters, then we're going to have 0.0015 meters. So in the end, we're just going to multiply by that 0.0015. So the real heart of this is that we are still just dealing with surface area. And we're going from -8 to 8. And we're dealing with part of a circle. Xanon? Did Xanon just walk by? And Xanon counts. So we are going to write the equation of this curve as a y value because we are rotating around the x value and this is a vertical distance, so we want to write it as a y value. And do you all see that if we have the circle of radius 10 centered at the origin, if we solve for y and we grab the upper half, that's what we're going to get. Square root of 100 minus x squared. So if we solve this for y, we subtract the x squared and take the square root, and then we choose the positive one, because we're dealing with the upper half of the circle, not the lower half. Okay, so same old thing. We know the ds is going to take a y prime and a y prime squared, and then a y prime squared plus 1. So we're just going to construct that inside, the inside of that square root. So the half comes down. We subtract 1 from the exponent. We multiply by the derivative of the base. That is our y prime. That's the derivative of the function. A little bit of simplification here. We can write y prime as negative x over the square root of 100 minus x squared. 2's cancel. A negative 1/2 power is a square root down below. And then we can take the square of this, and that will be x squared over 100 minus x squared. So there is y prime squared. So S, surface area. Let's look at the graph here and notice that there's actually some symmetry. So this curve is symmetric about the y-axis. We're going from -8 to 0 and 0 to 8. So we could just find half the area and double it. So let's do that. So let's put in a 2 for symmetry. So that 2 right there is because the curve is symmetric about the y-axis. And instead of integrating from -8 to 8, now we only have to integrate from 0 to 8. So this will give us half. And then 2 pi r. So r is that distance. That is the function. That's what the function measures. So square root of 100 minus x squared. So that's the 2 pi r. And then ds. ds is 1 plus y prime squared underneath the square root. Move that over for a second. Something's fishy. Okay, so 1 plus that squared. So 1 plus x squared over 100 minus x squared. Question?
You wouldn't take out the 2 pi?
Oh, we
The
can.
2?
Yeah, we absolutely will. Yeah, I just wanted to make sure that this 2 didn't get confused with that 2. So that 2 out in front is just the symmetry 2. Yes, 100%. So we'll have 4 pi out in front. And we'll simplify what's in here. And 2 square roots becomes 1. We distribute the 100 minus x squared, multiply it by 1. And then we multiply it by the second term, which will simplify to just x squared. Oh, once again, we have a whole bunch of cancellation here that ends up being 40 pi times the integral from 0 to 8 dx. So in here, these cancel. Square root of 100 is 10. 10 times 4 is 40. And then integral 0 to 8 of dx is 8. So we'll have 320 times pi. That will be final answer. 8 times 40.
Aren't you doing the paint, so you have to like multiply
Yeah.
still?
Yes, we'll still have the. So this is the surface area part.
Okay, got it.
Yeah, surface area part. And then our volume of paint will be 0.0015 multiplied by that. And whatever that simplifies to, this will be cubic meters. Yeah. So any issues on the surface area part? Today we get to do applications. Do a little physics. Yeah. Wrong applications? Not physics applications. Hopefully you're right ahead.
Always.
I should have warned you to read ahead on this section because this stuff is a little, yeah, complicated is the right word, but non-trivial. All right, 6, 7. This is the main application section the whole semester. Really the only one that is truly applications. So the first thing that we're going to talk about is this relationship between mass, density, and volume. Typically, when you hear density, you are thinking of mass per unit volume. So usually you see density written in that kind of form. Density, we use Greek letter rho. And we do mass divided by volume. So it's mass per unit of volume. So that's the classic kind of thinking of density as coming from volume. But there are situations where we're going to deal with one-dimensional density and two-dimensional density. So if you imagine a thin metal plate, then you're talking about density in the sense of mass per unit area. If you're talking about a rod or a wire, we're going to think about density as mass per unit length. So density could be in three different, depends on the context, could be three different scenarios. Now, the issue is that when density is not uniform, you can't just use our basic multiplication formula that we see here. If density is variable, so if along a wire the density is not uniform, if there's different densities at different points, or in a solid, different densities at different points, if the density is not uniform, then we need an integral to get to the mass from the density. If the density is uniform, you can just multiply and it's simple. But if density is not uniform, we have to integrate. And in the three variable case, if you had mass per unit of volume, you would need a triple integral, which we are not doing in here. That will be left for Calc 3. If you are dealing with the two-dimensional density problem, you would still have to integrate, but you would have to do a double integral to get to mass from density in a two-dimensional case. We're not doing that in here. So those two cases are left for Calc 3. The simplest case is if we have a wire or a rod and we have one-dimensional density, then all we do is integrate density to get mass. And so the concept here is very simple for us because we're just dealing with one-dimensional examples.
So from dimensional analysis, like what does one-dimensional density mean?
Mass per unit length. So it's going to be, so if we look right here, so this is going to be mass, oh, this is going to get ugly. Mass per meter. Let's use a kilogram, right? There we go, mass, kilogram. Okay, that's better. So this is kilogram per meter, and then this is a unit of length, so that's just meters. So you end up with kilograms. So this is a little kilogram. Add them all up and you'll get to the total kilograms.
I guess since we're doing applications, I'm trying to think of what
We'll
that
get to,
represents in the
we'll get
real
there.
world.
Yeah, we'll get there. We'll look at lots of units in a minute.
Okay.
Yeah. So if this was a triple integral, it would be kilogram per meter cubed, and your differential would be a dV, which would be meters cubed. And so you will get the units is definitely the place to look for all these applications, because if the units don't line up, then something's wrong. Okay, so for this piece, we're really just kind of focused on the concept here. These are not going to be on the exam. Integrating both of these, you know how to integrate those. So if this is the density function, we have a variable density function, then the mass is just the integral of this density function on the interval. So we're really just focused on the concept at this moment, nothing special here.
Can that be in the exam?
Exactly, yeah, sure, no. Okay, so plug in 0, we get 0. Plug in 1, we get 5/4. And they didn't even give us units on this one. So typically, mass, kilograms, possibly grams. Unless we're in the imperial system, then what would our units of mass be?
Stones, pounds, ounces.
Nope.
Slugs.
Slugs!
That's right.
Oh, banana slugs. So right, that's why we never use the imperial system. More than half of you probably never even knew that mass in the imperial system was measured by slugs. We always stick to the metric system, especially with these types of applications. Mass is kilograms. Kilograms or grams. What's that?
For foot pounds, actually.
Foot pounds for force, for work.
Yes.
Foot pounds.
Yes.
Not mass.
Yeah, it's close enough.
No. Then the mass here, we're going to integrate this exponential function. Again, 0 to 4, nothing special here. So we've got this variable one-dimensional density thing. Finding out what the mass of the wire, the mass of the rod is, all we do is integrate this variable density. And we have to use the reverse chain rule here. We have to divide by -2. And this is going to go 0 to 4. So that'll be our mass. Plug in the 4. Let's put this coefficient out in front and just do the e part as our antiderivative. So that's going to be e to the -8 minus e to the 0, which is 1. That is our mass. And that clearly is a positive number because mass can't be negative. Correct? Everyone agree that's a positive number?
Yeah.
Okay.
I don't understand how mass can be one-dimensional. That is a big stumbling
So just
block.
think about a very thin wire.
But even very thin, like you have atoms, they have width and length. and
You're
they're
such a
three-dimensional.
realist. Right? Absolutely, you could think that. You can think that way, but there's a certain moment where it's so thin that it doesn't give us any added value to treat it like it, like in reality. Where we can treat it as a one-dimensional quantity, and it's going to be just as effective.
So
Certainly, if we're
making
talking
it-
about like big tubes and a big cable, then we wouldn't want to do that because there could be a lot of variability between the density. If the diameter were 10 inches, that would be a lot of variability for the density possibly. But if we have a tiny thin copper wire, the density, if you were to cut it in half, the chances of the density being different on that tiny 1 millimeter, in diameter, not going to happen.
It's like asymptotes, how it gets like closer and closer to 0, and eventually it just suffices to say 0. Because
It's that idea, for sure.
tiny amount just isn't even going to matter.
So it's an approximation of
It is
something
an approximation.
that cannot exist.
Yeah, it's just like we round to the nearest penny.
Okay.
Right? Why do we do that? Because it's convenient. Is it true? No, the exchange rate actually has hundreds and thousands of pennies in it, but we just round to the nearest penny because it's practical.
Okay.
So it's that idea. In fact, pennies don't even seem practical anymore, right? We should round to the nearest nickel. Let's get rid of, they spend more money making pennies than the damn pennies are worth. It's like silly. And everybody agrees that's a positive number.
Yes.
Okay. So let's get to more sort of common applications that we're going to see in this section. Our next basic relationship has to do with work. And work is going to be force times distance. So in the simplest context, if you apply a constant force, so if we're dealing with metrics, we're applying force of newtons. We're applying some sort of amount of newtons. And if we move an object, if the force is in the direction of motion, so very simple, constant force, constant distance, you just multiply them. Of course, we want to get to a situation that's more complicated. So the next, to up the ante a little bit, maybe you have a force that's constant, but it's not in the direction of motion. So maybe you're pulling a wagon or something and the force is in that direction. Well, then the work is found by figuring out the... Do you guys pull wagons? So if you look at the magnitude of the force in the direction of motion, so we would say, okay, let's just look at the force in this direction. Then we'll find the length of the force in that direction, multiply it by the distance traveled. That's the next simplest case, which you do in Physics 1.
So engineering.
Engineering, yeah, pulling wagons. So
In the space.
now the thing that we are going to deal with more is just a pure up variable force. And if you have a variable force, then you have to use integration. And the idea is that if you were to zoom in on a tiny, tiny interval, the force is essentially constant on a tiny, tiny interval. So in a tiny, tiny interval, the force times the width of that interval will give you the work on that tiny, tiny interval. But then we do the Riemann sum. We have, number of intervals is going to infinity. We take the limit of our Riemann sum, and that's going to give us a definite integral. So the definite integral for us, we integrate force to get work. That is going to be what we do. Let's look at the units. What are the units of force? Newtons.
Nudie.
Newtons. dx is a unit of length, so that's going to be measured with a meter. So inside the integral, the units, including the differential, should match with the units that you're targeting on the left side. So everything including the differential should give you the correct units. And that's how we constantly are checking to make sure that we have all the stuff in the integral that we need.
That's newtons times what?
Meters,
Meters.
Newton meters or, pounds or.
a Newton meter. What's another?
Oh, never mind. It was a little off topic.
That's okay.
Do you know if this is what we use in calculus-based physics then?
Yes.
Like, is this pretty much what it is?
Yeah, this is what you would use. Absolutely. Integral of force to get work. What else can you use instead of a Newton meter? What's the equivalent? Joule. So a joule or a Newton meter, those are the same thing.
Joule.
Joules.
You
Joules.
said give another example. I did.
I said what's another, I didn't say another example. I said what's equivalent to a Newton meter.
Oh.
Foot-pound is not equivalent to a Newton meter. So do you guys say foot-pounds or pound-feet?
Yes.
Depends on if you're in England or America.
Yeah.
Is that true?
England, you
No.
say pound.
Is that
You
true?
believe it.
I've had to talk to
I mean, when I was taking physics in high school, we always said foot-pounds.
Foot-pounds.
And every example I look up on the internet of physics, they always say pound-feet now.
We say foot-pound.
You do say foot-pounds?
Yeah, I say
Yeah.
foot pounds.
That's
That's
not
put
foot
together.
pounds.
I said.
Huh. I was surprised when I was seeing all these pound feet.
I'm
Like, what's a pound foot?
Not
Okay, so our simplest work example is going to be with a spring. And the spring is the great introductory example because the force function, we integrate force to get work, and the force function is linear. Right? Integrating a linear function, what could be easier? Integrating a constant. Okay, never mind. So this is going to be the formula, Hooke's law, that is going to be the function that we integrate to get the work in compressing or stretching the spring. So that's kind of nice that it's a linear function. So with the spring, we're going to think about the spring at an equilibrium position, and then we're either going to compress or stretch it. And every spring is going to have its own spring constant. All right? Every spring has its own spring constant that gives you a measure of how stiff the spring is. So it's very similar to college algebra when you do those radioactive decay problems. Every radioactive isotope has its own unique decay constant. Same idea. Every spring has its own K. Same idea. So let's try one. Somehow we need to figure out K. Back in college algebra with those radioactive decay problems, the data point that they usually gave you was the half-life. And then from the half-life, you could figure out what the K value was for that particular isotope. Same idea. They have to give us a data point. And usually with springs, they're going to give us a force and a distance. Usually that's what they're going to do. They could also give us force and they could also give us distance and work. We'll see that in one example. But here they give us, they say a force of 15 newtons is required to stretch the spring 0.25. So that is the data point that they're going to give us. We know that Hooke's law is in play. So this is going to be 15 newtons is going to be K, times a quarter of a meter. So right away we can find K with that data point. We know that the K for this spring, no matter what, is going to be 60. That's the spring constant for this particular spring. So that is part A. So part A, what's the spring constant? 60. Part B says how much work is required. All right, so work is an integral. The force function is now 60x. For this spring, it's kx. Every spring, it's k times x. And it says how much work is required to compress the spring 0.2 from equilibrium. So it starts at equilibrium, and then we're going to compress it 0.2 meters. So that means with a spring, when you compress it, you're going in the negative direction. When you stretch it, you're going in the positive direction. So the position will be negative 0.2 meters. And then we integrate. And as you all probably suspect, if you compress the spring 0.2 or you stretch it 0.2, same work. It doesn't matter if you stretch it or compress it. It's going to be the same work if you're moving the same distance. Why? Look right there. Your antiderivative is a square. If that's plus 0.2 or minus 0.2, doesn't matter. You end up with the same exact answer. So that's going to be 0.2. We're going to write that in terms of, write it as a fraction, so that's 1/5. So negative 1/5 quantity squared. So we're going to get 30 over 25. Divide out the 5, so we're going to get 6/5. And we're talking about work, so joules or Newton meters will be the work done.
Could you scroll up?
Alex, how easy?
It's a spring.
Can it be this easy on the test?
If there's a spring, it can't be too much harder. You want a spring?
Yes.
Okay, so now the third part. How much additional work is required to stretch the spring 0.3 meters if it's already been stretched 0.25? Okay, so the spring is already stretched 0.25, so that's where it's starting. It's stretched to 0.25. And then it says how much additional work is required to stretch it 0.3 more. So we want to go 0.3 more, which is going to take us to 0.55. And then we have the same spring, so we have the same force function. So that's going to give us the work, the additional work. We don't know how much work it took to get to 0.25, but this will tell us how much additional work it'll take us to get to 0.55. Same antiderivative. Let's convert this over a quarter. 1.25 is a quarter. 55 100ths, divide out the 5, so we get 11 20ths. So this will be 30 multiplied by, square both of these. We'll get 121 over 400 minus 1 over 4 squared is 1 over 16. Common denominator of 400. Multiply top and bottom by 25. And then we just have to combine those. Whatever we get. So 30 multiplied by, what's that, 96? 96 over 400. And whatever that simplifies to.
Divide by 4, right?
Divide out of 4 for sure, cancel out a 0. 4 goes into there once. 4 goes into there
24, right?
24, yep. So 60 plus 12, 72 over 10. Does that look right?
Yeah, 7.2.
And then we're talking about work, so we'll put joules or Newton meters.
One of my questions is, how bad would you dog us if we, well, because does it really matter if we do, like when we solve our answers, does it matter if we have it in fraction form?
Well, the issue would be if your decimal is exact or not exact, because you have to find an exact answer. So if the answer was 1/3 and you tried to write it as a decimal or something comparable, it's maybe more complicated than a third. But so that's why we usually go with fractions, because that's an exact value. If you have an approximated decimal, you can't tell if it's exact or not. So that's why we always go to a fraction.
If you use the bar to indicate it's,
Yeah, you could do that.
is that considered exact?
Yeah, that's still fine.
Okay.
That's still fine. But what it, if there's a square root of 2 or
It's
a
like
pi, something like that, then. So there are ways to use decimals and indicate that it's exact, but typically we go to fractions because we know if there's no decimal point, you know they didn't approximate, right? If there's a decimal point, it's like, well, is there an approximation or not? And then you get into the, what are those horrible things called?
Sig figs.
Sig figs.
Sig
figs.
figs.
Ugh. Bleak.
Partial derivative.
Partial derivatives?
Uh-huh.
This is Calc 2. We just do the full derivative.
Okay.
None of this partial derivative stuff.
Stand by.
Okay, so let's try this one. So similar setup. It says calculate the work required to stretch the following springs 0.4 meters from equilibrium. Assume Hooke's law. So we have two different springs. So in part A, notice what they give us to find the spring constant. They give us a force and a distance. So it's very similar to the last one. So for part A, let's go with that one first. So for part A, they tell us that the force is 50 newtons, and that's going to stretch it 1/10 of a meter. And so pretty quickly, we can see that the K value for this spring is 500. And then we just want the work done in, what does it say, to stretch it. Wait, where are we? Calculate the work, stretch it 0.4. 0.4, okay, 0.4. I highlighted it for a reason. 0.4. So the work done, we're going to go from equilibrium, which is 0, to 0.4. And this is our function, our force function. So that's the setup for A. So we first find our spring constant, and then we create the force function, and then we integrate it. And so that's going to be 250x squared from 0 to 2/5. So that will be 250. 0 is great. And then 4/25. So we're going to get 40 joules. 40 joules of work. Okay, so that's the sort of classic way that you're given a data point to find the K value and then evaluate the work. So let's look at the second one. So the second one does not give us force and distance. It gives us work and distance. So here's how we're going to set this up. So we are now told that 2 joules of work, and we know that work is the integral of kx. We don't know the k yet. But that's okay. We can integrate this. K is a constant. We know that. So it's not going to actually affect the integration process. And we're told that we're going to go 0.1 meters. So that's another way they can indirectly get us to find K. They can give us a work value and a distance, and then we'll solve for K. So a little bit different, but this is easily integrable. X squared over 2. We're going to go 0 to 1/10 of a meter. I shouldn't put an equal sign, though, because we have an equation. Oh, my gosh. We have an equation there. So if we multiply both sides by 2, we'll have 4 on the left equals k times x squared. That's going to be 1 over 10 squared, so that's 100th. So the k value here is going to be 400. Any issues with finding that k value? Everybody see where everything comes from?
So work and force always go on the left,
Yes. Yep. I mean,
depending which one they give you though.
Yeah, depending on what they give you. Yes, yes, yes. And then once we have both, then work is on the right and force is on the, or work is on the left and force is on the right. Once we get the k.
Mhm.
Yeah, but to find k, yes.
Yep.
Yes. Okay, so now we want to do the same thing. We want to find the work done in displacing from 0 to 4. So the work will still go 0 to 4, 0 to 0.4, right? 0 to 0.4, yeah. And now our k value is 400, so we'll have a forcing function of 400x. And integrate that, calculate the work done. So this is 200x squared from 0 to 4/10, which is 2/5. So this will be 200 multiplied by 4 over 25. 8 times 4 is 32. So smaller k value, less work.
We just go up again.
Yeah.
To the questions.
Oh, to the question, yeah. So we want to find the distance from 0 to 0.4 for both springs. And for the first spring, they give us force and distance. For the second spring, they give us work and distance to get the K values. Yeah?
So with the K value for B, you just did like, you just put the value in for X and just algebra?
So, yes. Yeah, we plug in this value for X, yeah. Yeah. So here, the difference is that we don't know the K, but the K is a constant, so we know that we can pull it through the integral and it's not going to matter. It's kind of an alternative way to figure out what the K value is. That way is more common, but you certainly we'll see it that way also.
So is K force?
K is not force. K is a constant. If we want to figure out the units of K, we can, because we know that force is equal to K times X. So the force has units of newtons, and X has units of meters. So K is going to have Newton divided by meters. That will be the unit for K. So K is going to be newtons per meter for its units.
Per second squared or something like that.
Maybe. Maybe. All right, any spring question on there? Can we get to the pumping and lifting problems? Okay, so let's get to the pumping and lifting. So, again, we're going to have a basic relationship that we need to understand. And this is our basic relationship. That work is force times distance. So it's the same as it was in the last one with the spring. Here is the big difference. With the spring, the force was given by Hooke's law. All right? We didn't have any gravity. The spring is small enough, even if you have it this direction, it's small enough that you don't really need to consider gravity. Hooke's law is enough. So with these problems, gravity is going to come into play. So force is not just going to be K times X. Force is going to be mass times acceleration. So we're going to be dealing with 9.8 if we're in the metric system, 32 if we're in the imperial system. Most of these examples in here are going to be metric. So 9.8. Acceleration. So that's the big difference. So let's take a look at if we're lifting, if we're lifting or if we're draining. So if we're lifting or pumping, we are going to use this integral here, and it looks really messy. And if you look at all the units are going to match. I'm just going to jump to the next slide for a quick second. And what we want to do is analyze what's going on inside that integral. And we're going to need a really simple way to remember what goes in the integral so we don't have all these strange letters that seem unrelated. And so here is my recommendation. You can remember the symbols as they were in that example, but if we are finding work for a situation where we're draining a tank, that formula will always give you the right answer. What does it stand for? Acceleration, density, distance, and then volume. Not volume of the vessel, but volume of a representative slice of what's being pumped or drained. So a slice, just like we did with the volumes that we computed last week. So that will always give us the right answer. There is an analysis of the units, and of course they better match, and you can think about them and make sure they match. In a couple of days, we're going to do our last application, or maybe actually on Monday. Our last application will be finding force. Now let's just look at the difference here. So force is going to be, I'm going to use ADD area. Notice that there's just one dimension difference between the two. And we know that work is force times distance. So there's work, there's force. If we were to multiply by one more dimension of meters, then the area becomes volume. And we'd have force times distance equals work. right? So the units are all going to line up properly. And we'll talk about this one when we get to it. So this is pretty easy to memorize. ADD, however you want to remember ADD. Add is a math word. ADD, however you want to think of ADD. It could be something other than add. But that's what this represents here. That's what all these represent. It's just a little cleaner to write down ADD volume than that. Question?
What was volume again? It was area and what else?
What was volume is going to be area. Let me show you right here. So when we're talking about the volume, so when we rewrite this, one interval please. When we rewrite this, this is how I'm going to recommend doing it. So ADD, that's acceleration, density, depth, and that's what's up here too. There's acceleration. The row is acceleration, is density. So it's density and then acceleration, and then area times distance gives you volume, and then dy gives you length. But if we look here, if we do acceleration, density, depth, right there, or depth or distance traveled, you can think of that second D. Depending on the context, it could be the distance it's traveling, or it could be the depth beneath the surface of the water. So, and then volume is volume of the representative slice. So that's the volume of that layer of water. So if we want to find the volume of our representative slice, we find our cross-sectional area and multiply by dy. The way we turn area into volume is just to put the differential on it. That creates an element of volume. So that's going to be our plan. So we're going to pump out that element. We're going to find the work to pump out this slice of water, and then we're going to add them all up and get the total work to pump out all the slices of water. And so that's what this formula is going to do. So let's just not look at the individual units, but let's think more conceptually. We know that force is mass times gravity. And we also know that density times volume is mass. So let's look at this one first. There's density, and area times distance is volume. So right here we have density times volume. Density times volume is mass. So the yellow stuff there is mass. And then mass times acceleration or mass times gravity, that is going to give us force. And dy is a little vertical distance, so that has units of meters. So now we have this whole thing right here is force, and that is distance. So that's how the units are all going to play out. We're always going to end up with force times distance inside the integral. And so our units are going to match perfectly. And now that said, you can, in practice, when we look right here to this area, that's our cross-sectional area. Really, the volume that we're talking about is combining it with this thing. Like the A of y is a cross-sectional area, and if you multiply by dy, that creates your slice. But it doesn't matter how you group these. This distance function has units of meters. This differential has units of meter. Like it doesn't matter if you know which one, you can pick and choose. When we're visualizing this formula, we're thinking of the cross-sectional area multiplied by dy to get that volume. So that's an elemental volume. It's not the volume of the whole thing. It's the volume of our slice. All right, so let's go ahead. Let's take our 10-minute break, and then we'll do an example of this afterwards.
All right. Can I see that page of the ADD?
Tank, we have a cylindrical tank, and we want to figure out how much work it takes to pump the water right out of the top. So it's just going to come straight out the top. And let's take that off. And what we want to do is sort of focus on a representative cross-section that turns into a representative slice. So let's just suppose that we draw our representative slice right here. So this is a slice. So it's going to have thickness to it. It's going to have the dy. We're going to say that this is the slice at a height of y. Cross-section at height of y. All right. So let's write down our formula and then fill in all the blanks. So we know that the work, if it's work, it's going to be the integral of ADD volume. And so inside the integral, it's acceleration, density, distance, or depth. In this case, distance makes a little more sense. Or you could think of how far down in the tank it is. So however you think about it. ADD, acceleration, density, distance. So acceleration, 9.8. Density, 1,000, because we're dealing with water, so that's given. So almost all of these are going to start out with 9.8 times 1,000. So now we have to think about the next stuff. So acceleration, density, distance. And that distance means the distance your representative slice travels to get out of the tank. So if we're pumping right out of the tank, that is the distance that's traveled. This is going to be your second D. Right, so that slice is traveling how far? 8 minus y. So this distance right here is y. This distance right here is 8. So that distance right there, 8 minus y. That is the distance the slice at y has to travel. 8 minus y. Now we come to the volume part. This is the volume of our slice. So we look right here, there's our slice. The volume of that slice, well, it's the area of the cross-section multiplied by the thickness, which is dy. And what is the area of the cross-section right there?
2 pi.
So the radius is 2.
So
Area is pi r squared, so 4 pi is the cross-sectional area. So 4 pi, and then we multiply by dy. So that is the volume. It's the volume of the slice, not the volume of the tank. That's it. And then we have slices of water, cross-sections of water, from 0 to 8. So the upper limit will be 8, the lower limit will be 0. And that is the setup. So again, I think having an acronym process to remember this, how this works, makes it pretty reasonably easy. I mean, not trivial, but certainly not as hard as looking at the generic formula. So then we can factor out the 9,800, we can factor out the 4 pi, and all that's left in this integral from 0 to 8 is 8 minus y. And I'll just leave this unmultiplied out for a moment. Maybe we'll get some cancellation after we integrate. So we integrate term by term. That's 8y minus y squared over 2 from 0 to 8. So we'll come over here. We have 9,800 multiplied by 4 pi, multiplied by plugging in 8 gives 64 minus 32, so 32. And whatever that multiplies out to. I brought a calculator too. So I'm getting 125,440. So multiplying it out, we get that, 1 million and change times pi, joules. Okay, so basic procedure. Look at a representative slice, figure out how far it travels to get out, fill in the blanks, ADD volume. So let me ask a related question. What if, instead of pumping straight out here, what if we had a 5-meter pipe up here and we were pumping it out up there? So we still have a tank full from 0 to 8, but instead of pumping it right over the lip, we wanted to pump it 5 meters up higher. What would change?
8 plus Y?
The 8 minus y and the 0 to 8.
The 0 to 8 will not change because we still have physical slices of water from 0 to 8. But the distance those slices travel would be different. What would it be?
Oh, we're not adding water to the top.
8
I see.
plus Y or something?
16. Or wait, how much are we?
What's
Oh,
8 plus 5?
13.
13. So 13 minus y. So the distance would be, the full distance would be 13 if we're going to go 5 meters above the 8. So the distance each slice travels is going to end up being 13 minus y instead of 8 minus y. But we still physically have 0 to 8 in terms of the water. So the limits won't change.
So nothing changes if it passes through a smaller pipe? We don't have to account for the smaller slice area?
Yeah, because the work done is only going to depend on how far it travels.
Okay.
So it might take a little bit longer to get through it because it's funneling, but that's not going to change the work done.
Okay.
So what about if we had the tank half full? So let's suppose we're still pumping out the top, but let's just suppose the water level is only 0 to 4. What changes?
The limits.
Just the limits. The distance is still 8 minus y if we're going to pump straight out the top. So that wouldn't change. All right, so let's change the look of the tank. Let's suppose we have a trough now. And same idea. We're going to suppose it's filled with water. We're going to pump it right out of the top. See what happens. So our formula, we know that work is going to be the integral of ADD volume. All right, so that's our generic formula. And when we're thinking about our representative slice, here, our representative slice, we're going to come right across the front, and a slice of water is going to have what geometric shape? A rectangle. Right, that is a cross-section or slice of water. It's a cross-section if it's two-dimensional. If we add the little thickness, the dy, then it becomes a slice. So there it is, right there. Let's draw let's look at the face of our trough. So it's a semicircle, and that representative cross-section is right there. Okay. So let's start filling in the blanks. So we know that we're going to have a 9800 is going to come to the front like it always does with these. A times D, 9.8 times 1,000. 9.8 times 1,000. And then this D is the distance traveled by your representative slice. And how far does that slice have to travel?
0.25 minus 1.
Did you say 0.25 minus y?
Yes.
Yes. So this semicircle has a radius of 0.25. So that means that this distance right here is 0.25. And we are going to put the slice at a height of y, which means this distance is y. So that means the distance it travels is 0.25 minus y. So that will be our distance right here, 0.25 minus y. So I'll write it as 1/4 minus y. Okay, now volume. Now we're talking about the volume of our representative slice. We know the thickness right away is dy. The cross-sectional area is just a rectangle, so it's width times length. And we know the length of the rectangle is 3 no matter what. So the only thing we need is the width of our rectangle, which is right across the face here or right there. We need that width. This should look like a lot like that problem we just looked at during the break. We need the width across a semicircle, the chord length across a semicircle. All right, so let's figure out a coordinate system. So the coordinate system I will choose is I'm going to put the trough right on the x-axis. Sometimes folks will put the coordinate system so that the coordinate system has got the origin right there at the center of the circle. I would prefer to integrate from 0 to 1/4, not from -1/4 to 0. If you do the center if you do the origin right there at the center, then you're going to be integrating from -1/4 to 0, which I prefer not to do. You could do it that way, totally fine. I'd rather integrate from 0 to 1/4. Again, does not matter. So we need the equation of this circle here. This semicircle is going to come from a circle. And the center right here is at 0, 1/4. The equation of a circle, you should hopefully know by now. X minus h quantity squared plus y minus k quantity squared is equal to the radius squared. The radius is 0.25, so we square that, we get a 16th. So that is the equation of that circle that's been shifted up a 1/4 unit. The x values of the center is 0, so it's x minus 0 quantity squared plus y minus 1/4 quantity squared. Now, what letter are we solving for here? We're going to solve for
X.
same reason as before, right? That element's horizontal. If you're trying to find a horizontal distance, it's x minus x, so you need your functions written as x values. X value on the left and x value on the right. So we need to solve this for x. So x will be plus or minus the square root of 1/16 minus, we'll FOIL this out, that's y squared minus 1/2 y plus 1/16. Foiling. So this will be plus or minus the square root minus y squared plus 1/2 y. The right half of this semicircle, is it the positive or negative? Positive. So that's going to be x equals positive square root. And the one on the left is the negative. So let's call the entire distance across that chord, the length of that green segment there, we'll call it W. And what is W equal to?
Right minus
Say that again?
right minus left.
Right minus left, so what do we get in for our final W?
2 square root of negative y squared plus 1/2 y.
Thank you. So it's root minus minus root, which gives you 2 roots. Or you can say to yourself, this function here is measuring half of W, half of the chord width, and double it. Get the full chord width. So that is the width of our representative slice. It's a function of y. Right? It depends on how high you are in the trough. When y is 0, your width is going to be 0. And then when you get up farther, the biggest your width is going to be is up here at the top. So let's fill in our blanks here. So we have 2 multiplied by the square root of negative y squared plus 1/2 y. Can I get that little dot? Oh, wow. So that whole thing, here is the area of the cross section, and then volume of the slice. The area of cross section is just the area of a rectangle, width times length. Multiply by dy to get the thickness, that turns it into a tiny volume. And what would our limits of integration be?
What's the problem? 0 to 1.
Same problem.
Oh.
It's one we've been working on. So the semicircle has radius 1/4, so 0 to 1/4. All right. Let's pull our constants of integration out. So we have the 9800 already out there. We can pull out the 3 and we can pull out the 2. I'm going to pull out the 3 and leave the 2 for a reason. What technique of integration do you think we're going to probably have to use here? U sub. We've got a square root. We typically will let u be what's inside the square root as our first go. And what is the derivative of what's inside that square root?
Negative 2y plus 1/2.
Negative 2y plus 1/2. And so what we've seen with substitution is that we want the derivative of whatever we let u equal. We'd love it if that derivative were right out in front. And when we look right here, that's almost the derivative of what's inside. And it will be the derivative of what's inside if we take that 2 and we distribute it right there and make that 1/2 minus 2y. So we'll take the 2, we'll leave the 2 inside the integrand because it can then create exactly the derivative of what we're going to let u be. Do you have to? No. If you pulled out the 2 and you found your u and you took the derivative, you'd end up with an extra 2 in the denominator somewhere. It's not going to matter. But this will just make it a little cleaner. So why don't you all start doing the u substitution here, let u be what's in the root while I take roll. And Jill. Were you here last time? Yes. Oh, yeah. Every time. I remember that. Logan. Alex. Araceli. Have you ever met another Araceli? Have you?
Yeah, but sometimes instead of a Y at the end, it's an I.
It's such a cool sounding name. This Dan. Oh, the other Dan is not here.
Did he go to the morning class?
He was not there yesterday.
Maybe he just said, screw this, I'm working at Walmart.
Huh? All right, Mr. Garcia is not here. James is here.
Today's the drop deadline. Yeah.
And Mr. Jones.
Fact check tree.
Ian. Joseph.
Here.
Joshua. Were you here last time?
No.
Okay. I didn't.
This right here.
I just had trouble
Did you
getting here.
use that or? No, I'm fairly strong.
It'll never happen again, right?
No.
Car issues?
No, it's just like, there's just no way outside.
Oh, yeah.
And then I
Weather
take the
issues.
derivative,
Jordan.
And it matches the other.
Gerardo.
What?
What?
Frederic. JP.
Times
Yeah.
3.
Hannah.
Here, 2.
No Hannah, right? No Hannah.
1/2 T.
Dustin. Adriana.
I got
Riley.
negative 2y plus 1/2.
Dante.
Square root.
Caesar. Cole.
Yeah.
Oh, you can't do that.
Wait, not just 1/2.
Roberto.
You let me visualize that problem.
You put
Eliana.
in 0, 0.
Celeste.
Square root of 3.
Eliana. I can't remember what she looked like.
I don't know.
How's that U sub coming?
I'm struggling at it.
Oh, really?
You just use the
All right, let's try it.
No.
You know, it's negative y squared.
I'll put it over here.
You know what I mean? I think just, I don't think it is. I don't think it is. So it's plus.
Mr. Bob,
So, yeah.
quick question.
Yeah.
So it's 0.
Negative a half plus 1 is 1/2, right?
100%.
Okay. I don't know why I couldn't.
You are not crazy.
Debatable.
Debatable.
Other heavy tests.
So, everybody agree with that U sub up there? We're going to let U be what's in the root. We take the square root. And what comes out very nicely, like we said, is that inside here, we just have U to the half du. Right, the u is what's in the root, so we end up with u square rooted, which is u to the half. And then this whole chunk, minus 2y plus half dy, that whole piece right there, that's all du. What's that?
Never mind.
Now we have to convert our limits. Our limits need to become u limits. So we look at our y limits. When y is 0, we come right up here. This tells us how to get back and forth between u and y. When y is 0, u is 0. And then when y is a quarter, we come up here. Minus a quarter squared, that's minus a 16th plus an 8th. Minus a 16th plus an 8th is plus a 16th. So those are our u limits. And then we can roll. And we can multiply this out in front, or we can just wait. Sometimes we're going to get cancellation based on whatever this antiderivative is. So we're going to have u to the 3/2 multiplied by 2/3. And that's going to be 0 to 1/16.
If I went back and back substituted, would I have to change or no?
Yeah, if you're going to do that, you don't have to change.
Okay.
If you're going to go back to y limits,
Yeah.
you do. Plugging in a 16th, let's see, the 3's cancel here. Plugging in a 16th, the square root of a 16th is a quarter, 1/4. And then we have to cube it, so we're going to have 1 over 4 cubed. 4 cubed is 64. 4 times 4.
How did you get the u limits again?
Yes, so the u limits are coming from right here. So when we do our substitution, the substitution is what relates u to y. So we're going to take whatever these y limits are, since that's a dy, that means these are both y's. We plug them both in here, and that's how we'll get the u's. So plugging in y equals 0 gives 0. Plugging in y equals 1/4 will give us 1/16. So right from the substitution statement. And then, whatever that turns into, 9,800 divided by 32. Change it to a fraction. $12.25 over 4 joules. Question?
When you were solving for the semicircle,
Mhm.
where did you get the 1/16?
This 1/16 here,
Yeah.
foiling. So this, when we foil that, we get y squared plus 1/16.
Yeah, but it says that equals 1/16. Where did you get the?
It's the radius of the circle.
Oh,
Oh, that 16th there?
yeah.
Radius of the circle is 1/4, so 1/4 squared, r squared.
Oh, that makes sense.
Yeah, x squared plus y squared equals r squared. So the radius is 1/4, so squaring the 1/4 gives 1/16. Yep.
I want to know where'd you get your limits in the integral for 1/16 and 0?
That?
Yes.
So that is coming from taking the y limits and plugging them in right here. Plugging in 0 gives 0. If you plug in 1/4, 1/4 squared is minus 1/16. Plugging in 1/4 here is plus 1/8. Plus 1/8 minus 1/16 is 1/16.
There you go. That's
You gotta know your
it's
tools.
easier.
You gotta know your tools.
Yeah.
I gave you the simplified answers now, right?
What's that?
I gave you the simplified answers now, right?
Sure.
Okay.
Why not?
Because that's how Y gave me it, and I don't want to back convert that.
Yeah, that's totally fine.
All right.
Chaos theory.
Let's do a cone. So same ideas. Same ideas. We're going to think about a representative slice. And what is the geometric shape of our representative slice?
Triangle. Circle.
Circle. Thank you.
Circle.
Circle. We are slicing horizontally where gravity is constant and distance is constant for the distance traveled by each particle of water. So there is our representative. We're going to say a representative slice at y. How far does that slice have to travel?
6 minus 1.
6 minus y. What is the area of this slice? We know that we're going to have to get the area of that cross section to build the volume of our slice. So that's a circle or a disk,
Pi r squared dy.
correct? So what letter? What's R in terms of y?
What?
Oh, you slowed down.
Yeah.
What's R in terms of y?
Yeah, well.
R in terms of y? Anyone see it? So do you agree that if we think of this line right here and we think of a coordinate system right there, we could find R? So is that that's a horizontal distance? So if we know the equation of this diagonal line and solve for x, that'll give us a horizontal distance. And this line is just a line through the origin, so it's y equals mx, where m is slope. And what's the slope of that line?
X over 1.5.
What was the
2.
slope?
Is that 2?
Not 2, I don't think.
X over 1.5x.
Which is? 4. Yeah, so that's the equation of that right edge then, y equals 4x. You agree? So rise is 6, run is 1.5. So 6 divided by 1.5. Is that the hard part? 6 divided by 1.5?
Well, initially I had thought it started at the other edge of the cone. I didn't realize, and once I realized,
So yeah, this,
Yeah.
right, yeah, that, okay.
it took me a moment because I couldn't see it.
Yeah, it can take a moment for sure. So everyone agree then, 4x? And if we solve for x, that's r. So x is going to be y by 4. So that is the radius. That is going to be the radius. So this tells us the radius at a height of y. So if y is 0, the radius is 0. If we're way up here at the top, if y is 6, 6 divided by 4 is 1.5, 3/2. So that allows us then to fill in all of our blanks for the work. So work is going to be integral of ADD volume. Okay, so we have, once again, acceleration, 9.8, density, 1,000. So we're going to have 9,800 out in front.
What was
then-
the problem again?
What's that?
What's the problem?
How much work
Which way?
to pump it out the top? The work, good question. The work done in pumping the water out the top is the same as the work done draining it out the bottom. Same work. It's just that when it comes out the top, the pump is doing the work. When it drains out the bottom, gravity is doing the work. But it would be the same amount of work. So if you wanted to, you could sort of invert your thinking and you could turn it into a drain problem and figure out how much work gravity is doing draining it out the bottom. That would also work.
So from 6 to 0?
So you would integrate from 0 to 6 in either case. You don't you don't upside down the tank.
I can't tip the tank over.
There's still slices of water from 0 to 6,
Why
whether
can't
you're going
you
out the
repeat
top or out the bottom.
Why can't I kick the tank over?
If you could do that also, I guess. So you're going to go 0 to 6, and then so we have our AD done, and then this is our second D. So 6 minus y.
Sucks so much.
Okay, now volume, pi r squared is that cross-sectional area. So pi r squared, and we found our radius to be y over 4. So there's pi r squared. And then the thickness of our cross-section is going to be dy. So
The 9,800 comes from the gravity, right?
that comes from gravity and density of water. So the density of water is 1,000, and gravity is 9.8.
Can we take that 16 out or no? Hide 16.
Absolutely, 16 will come out.
Fancy P. Yeah.
The fancy P, rho, yes.
Rho.
That is density. So 9,800 times pi divided by 16. And I think the only thing left in here is 6y squared minus y cubed.
Cute.
How come in this one we used pi r squared to find the volume, but in the previous one we did like the whole other like long process?
So it all depends what your cross section is. So the cross sections here are circles. So pi r squared is the area. The cross section here is not a circle. The cross section is a rectangle. You see it?
Yeah.
So cross section, if we look at the face of the trough, cross section is this direction, and we go all the way back, that's going to build a rectangle. So no pi for a rectangle, just width times length.
But we did like a very long way to find the length, because isn't the radius, wouldn't it be like, couldn't you do 1/2 times 3?
No, because the front here, the width of this rectangle
Oh,
is
yeah, because it changes.
it changes. Yes, yes. Yeah. That's right. So then we end up with just that. And so let's just see, maybe we'll get some cancellation. We'll combine these numbers later. So that is going to be y cubed over 3. So that's going to be 2y to the 3 minus y to the 4th over 4 from 0 to 6.
That's the 4 and the 2. Oh, bye-bye.
So then we'll plug in our upper limit.
216.
So 6 times 6 is 36, times 6 is 216. So we have 2 times 216 minus, here we have,
What's 216 times 6?
yeah, we have, let's not do it. let's be creative. So do you agree with that? If we have 6 to the 4th, we could do 6 cubed is 216, and we could factor out the 216. So we have 9,800 pi 16, and then we factor out a 216. And then we're going to have 2 minus 3 halves. 2 minus 3 halves is 1/2. 2 minus 3 halves is 1/2. And so we've got that. That thing is, that's not divisible by,
That's 32, nice.
that's not divisible by 16, unfortunately.
About 32.
All right, so then we just have to plug it in.
Multiplication signs or
9,800.
decimals?
What's that?
Are those multiplication?
Take a guess. Do you see any decimals?
Can't tell.
They're multiplication. They're multiplication. Yeah, we'd be doomed if those were decimals. 9,800 times 216 divided by 32
Times pi.
times pi.
Times a half.
Somebody else confirm?
Yep.
The arithmetic. Okay, so, and our units are joules because we're finding work.
Would you always say to not factor the pi in so we have an exact answer?
Yeah, exactly.
Yeah.
So we won't approximate it unless, and sometimes my math lab will say approximate to the nearest tenth or nearest unit. Then you would put in the 3.1415.
Yeah, okay.
Dan?
So just circling back, when you said we could invert it and envision it as draining, and it would
Not
be
invert the cone.
Well, invert the
Process.
Yeah.
So we can think about it draining out the bottom instead of coming out the top.
So
So
why
let-
would more work not be done, applying force against gravity?
Oh, I misspoke.
Okay.
If it's a cylindrical tank, if the tank is symmetric from top to bottom, then it's the same work going in and out. So if you have a cylindrical tank, yeah, I oversimplified that. For a cone, it's going to be a little different, right? Because the thicker slice or the bigger slices up here travel less distance when they go out the top. And if they come out the bottom, the bigger slices would have to travel further. So there will actually be more work done draining it than pumping it out the top. Yeah, I totally jumped the gun there. If it's symmetric, though, like a cylinder, then the work draining out the top or coming out the bottom, whatever. Both are going to be the same. But if the tank is like this, it's going to be more work to travel all that stuff down at the bottom. So for the trough that look like this, it's going to be more work also to drain out the bottom because the top is wider, and less work to come right out the top because the bigger slices have less distance to travel. Yeah, good. I'm glad you said that. Jumped the gun. Does that make sense to everybody? Yeah. So, was that a yes or a no?
No.
It's a questionable, like,
It's a marginal yes.
I'll take your word for it.
I'm still just imagining like going in with a scoop and scooping out water on the top.
Okay, you
I
can
don't
imagine that if you want.
I don't understand
That's
that.
not how I imagine it, but why don't you use a teaspoon?
Sure.
Do it delicately.
66,000 times.
66,000 times. All right, let's go to the rope. Because this is, so this is a sort of a slightly different case. So a rope or a cable. So we're going to page 7. So notice this little note. Note the note. Note the note right here. So note the note. When dealing with one-dimensional density, there is no A of Y. So if it's one-dimensional, we're thinking of a wire or a rope or a cable. We're thinking of it as so thin that there's no cross-sectional area. We're doing one dimension. So then the A of Y factor is not there. So let's go to page 7 here for the rope. Actually, it's on this page 6 thing, right? Oh, no, it isn't. No, it's page 7. Okay, so page 7. So here we've got a 60-meter rope. They tell us the diameter is 9.8 millimeters. Ropes got thinner than they used to be. And it hangs freely from a ledge. So we've got this 60-meter rope hanging like that. So 60-meter rope hanging off the ledge. Now, notice density. Is that a 1D density or a 3D density? 1D density, which tells us instantly that we're dealing with a one-dimensional case, so this diameter is completely unnecessary. Right? If the diameter of the rope mattered, then this would have to be given in grams per cubic meter. It would have to be given in 3 dimensions, which we can't do yet. So, all right. So the density, let's come over here and look at the density. 55 grams per meter. We want to be dealing with newtons. And so we want things in meters, not centimeters. Or kilograms, not grams. So how many?
1,000.
1,000. So we're going to multiply, we're going to divide this by 1,000. So we're going to have 55 over 1,000 kilograms per meter. And if we divide out the 5, we're going to have 11 over 200 kilograms per meter. So that will be the one-dimensional density. Yeah?
I'm sorry, where'd you get that 1,000 conversion?
Number of grams in a kilogram.
Okay.
Right, so 1,000 grams is 1 kilogram. So we're going to cancel out the G's and get kgs. Okay, so here reiterated. Instead of volume, we only have length because we're taking away that cross-sectional area. So all we have is length. Length in this case is just dy. That's the little length of rope or cable or whatever. So this formula simplifies quite a bit. So work will be, I'll write it again just for the heck of it, ADD length. So acceleration is 9.8. Density is totally different though, right? We're not dealing with water, so we don't have that 1,000 tossed in there. That's our density. 11 divided by 100. No, 11 divided by 200. So that's acceleration density. Now we need distance, so let's look at our picture. So in all of our other things, we did a cross section and then turned it into a slice. Here our cross section is only one dimensional, so it's really just a point. So there's our cross section. And then we add the thickness, which gives us a little bit of height, dy, a little bit of height.
60 minus.
So this is going to be the cross section at a height of y. So the distance traveled by this segment of rope or this element of rope, how far is it traveling? 60 minus y. Right, this distance right here, this height where it's living is at y, but if we're pulling it up, the distance it's going to travel is going to be 60 minus y.
The swinging.
The green is the rope.
The green is the rope. Yeah. The red is the cliff, the green is the rope, the blue is the analysis.
Can you just make it a goat?
What?
Just be
Make it a
pulling up-
what?
Pulling up a goat.
A goat?
Yes.
How much does the goat weigh?
I don't know.
What's the density of the goat?
A goat?
Zero density goat.
Yeah, have you guys gotten sucked into those goat TikToks? Oh my god. My wife sent me this goat TikTok, and of course it was totally cute, the sweet little furry goat, and all of a sudden I'm getting all these goat TikToks now. Goats all over, cute goats.
Are you okay?
I know, it feels a little disturbing to me. All right, so now we know that the length is 60 minus y,
DY, right?
and dy is the length. So dy, length, don't get sucked into thinking length means the length of the rope. It just means the length of your element. Now, let's talk again about the work thing where we said there was some symmetry with the cylindrical tank. There's also symmetry here, right? The rope is symmetric, and the same amount of work will be done dropping the rope, but the work would be done by gravity. So if you drop the rope, work done will be the same. And if you did drop the rope, what would the distance the element of rope at height y travels?
Y minus 60?
No.
Y minus
If it's at a height of y and you drop it, how far does it travel?
Y.
Y. If you just replace this with y, you'll get the same answer.
Okay.
Right? If you replace that with y, because that will be how far, that will just change your perspective to dropping the rope instead of coiling the rope up. But you'll get the same answer in this case, because there is the symmetry thing going on. All right, what about our limits of integration? 0 to 60? We have segments of rope from 0 to 60 that need to be hoisted. All right, so out in front, 9.8 multiplied by 11 divided by 200. And then we integrate, so we'll have 60y minus y squared divided by 2, 0 to 60.
3,600 minus.
So 9.8, I'm just going to do that first part. 9.8 multiplied by 11 equals, oh, nothing nice.
107.
Divided by 2, yeah, exactly, 0.8. All right, change that to a fraction. So the stuff out in front, those three numbers turn into 539 over 1,000. And then in there we get 3,600 minus 1,800, which is 1,800. So we end up with, two of the zeros cancel, we'll get 539 multiplied by 18. And we get 9,702 divided by 10, I believe. Canceling out a pair of zeros and a pair of zeros. Somebody confirm that? Joules.
Less than 1,000 joules. Now we're pulling up 55 grams.
The density is 55 grams. We don't know we could find the mass by multiplying the density times the length.
Good.
Okay, so any questions on the concepts with that example? Do a couple more.
Well, could you show how doing y instead of 60 minus y yields the same answer?
Are you that curious?
Very.
very curious. Hopefully I'm right. So 0 to 60, we'll still have 9.8, we'll still have 11 over 200, we'll still have y dy, or we will have y dy. So this piece here, that constant, that's going to be that number right there. That's all that. So 539 over 1,000. Multiplied by, we integrate this, we get y squared over 2. 0 to 60. And this will be 539 over 1,000. Plugging in 0 gives nothing. Plugging in this is 3,600 divided by 2, which is 1,800, which is exactly that.
Okay.
Right? So if you prefer to integrate just y instead of 60 minus y, there's a shortcut.
Okay, thank you.
Yeah, absolutely.
So let gravity do the work.
Let gravity do the work.
So for coiling a rope here, what would ADD represent?
So when we're coiling it, it's representing what it has been representing all along. It's going to be acceleration, density, distance. Acceleration, density, distance. So it's representing force.
Okay.
Right? So when we look at a work integral, work is always force times distance. So this would be force, and that little dy is distance. So the ADD part, because that's everything except the differential, that would represent force. All right, let's try another one of these ropey chain things. So 30-meter chain hangs vertically from a winch. Assume there's no friction. Chain has density 5 kilograms per meter. Right there is where we notice that it's one-dimensional and not three-dimensional. When they give us the density, we know that if they gave us a diameter of the chain or the rope or whatever, it would be insignificant. We wouldn't need it. Okay, so density.
And we don't have to change it, right?
No, because it's given as kgs already, so we don't have to convert it. So how much work is required to wind the entire chain onto the cylinder using the winch? So we know it's a 1D lifting problem, so the work done is going to be ADD length. So that's our starting point, is to get our generic formula. So that's our generic formula. Acceleration is due to gravity, so that's going to be 9.8. The second letter, that D there, acceleration density. Density is 5. Now the third letter, the second D, that's the distance traveled by an element of chain. So we've got this winch up here. There's the chain hanging 30 meters. And if we take an element of chain right there at a height of y, the distance it travels is 30 minus y.
Is it the same thing where you could cheese it?
Yeah, that's the same idea. So the distance traveled is 30 minus y. So that is going to go here. So there's our ADD. And what do we put in for length?
dy.
Just dy. dy, that's all we put in. And then this is going to go from 0 to 30. So that'll be our work. So we'll have 5 times 9.8. So that's 50 minus 1, 49. 50 minus 1, 49. And then we'll integrate to get 30y minus y squared over 2. 0 to 30. So plugging in the 30 gives 900 minus 450, so 450. So we'll have 450 times 49.
22050.
22050 joules. And this would be the same if we replace the 30 minus y with y. It would be the same. All right, you ready for a mystery? No?
50 kilogram block attaches to the.
Do I have an option?
Oh, we're not done with this one.
Yeah.
Okay, we'll do the mystery next. All right. So the second part says same scenario except that we have a 50-pound block. If we have a 50-pound block, we can treat the block as a separate scenario. We can just talk about lifting the block 30 meters. And we know that if we have, if this is just going to be lifted, we can just use MGH. If we just have a block and there's not this different distance traveled by each part, like when we're doing the pump thing, you know, each one of those slices travels a different distance. When we're looking at the chain, each segment of chain travels a different distance. But if the block is like a point mass, the whole thing just is lifted. So we can do MGH for that. So for just the block, the work done is going to be MGH. And so that's going to be the mass is 50 kgs times gravity, which is 9.8, times distance traveled, which is 30.
1470.
Say it again.
1470.
1470.
Sorry, that extra zero at the end.
That?
Yes.
So that is the work done just to have a block of 50 kgs lifted 30 meters. And so then what do? Just add those two. So our total work will end up being whatever these two add together. Looks like 36,750. Okay, ready for the mystery?
I have a question.
Oh, there's a question. She's delaying the mystery.
So, why were we able to do that with the block, but not with like the chain?
So with the chain, each piece of chain travels a different distance. So the integration is taking care of, so if each piece of chain is traveling a different distance, we have a force times distance for each one of those. So there's a variable happening with the distance traveled. With the block, we're imagining it as just one point. We're imagining it as a very dense block. And so it's like one point is being lifted as opposed to an infinite number of points being lifted. Does that make sense?
Yeah.
Okay, mystery time. So, suppose we have a 40-meter chain. Density, we'll just pick it to be 1 kilogram per meter, and it's hanging from a winch. How much work is required to wind it halfway? So there are two ways to do this. So we're just going to wind it up halfway. Let's look at this image here for this one. And this one I am going to call the reality method. So we've got our 40-meter chain, and we're going to wind it halfway. So the orange links, when we're up there winding it, the orange links get wound up onto the winch, and the lower half of the chain, the black links, they're there. Right? That's where it starts, that's where it ends. This is just like the block problem, because the block problem is, you could imagine this cable just being, you can figure out the mass of the cable here, and you could do this problem exactly like we just talked about doing with the block. That would also work. Because these are not traveling all the way up to the top, you could treat this as just a dangling block, and you'll get the same answer. So here's the way that we would set this up. Let's look at this first scenario here, and then we'll look at the quantum perspective. So when we are doing this, we're going to treat it as two separate problems. We can imagine winding up the links from 20 to 40 ADD length. So this part right here is the orange. All right, so that's in reality what's happening. The links from 20 to 40 are being wound up to the top, and then this whole chain is just being lifted. Like it's dangling here, it's dead weight here, it's still dead weight here. We could figure out the mass, multiply by G and H. This would give us the block, or the lower part. So it's Either way, you're thinking of it as the links or as just a block, we'll give you the same answer. So that's how I did it the first time I saw this problem in this book. And I got the answer, and it was the right answer. But then I looked at the way they did it, bless you,
Excuse me.
and this is how they did it. They did it with that one simple little integral, and I was totally befuddled by why that would be. So here, what they did was said, okay, we've got the chain hanging. Here's the initial state. And the terminal state, there's half a chain hanging, but instead imagine that all you're doing is taking the lower half of the chain and lifting it up, and you're letting the top half just stay the same. That's what this does. This says, let's take all the links from 0 to 20 and figure out how much work is done in the work done in moving all of them up to here. And that's what that does. This does ADD length, so it's doing the 0 to 20, the distance traveled. So here we're imagining our y is being down here. How far are those links traveling?
Y plus 20?
40 minus 1.
Or,
I would do it as 40 minus y. 40 minus, because y is this distance here. That's your y. So the distance that link travels is 40 minus y. And it's all these links between 0 and 20 that are going to travel the 40 minus y. Whereas up here, you your y is up here. It's still going to travel 40 minus y. These are going to travel 40 minus y. It's just that these are traveling 40 minus y, but the links are from 20 to 40. These are traveling 40 minus y, but they're from 0 to 20. And you will get the exact same answer in both cases. So this I would call the initial state versus final state. You're sort of looking at where it starts and where it ends, and we're just saying, hey, we could imagine, even though it's not true, in reality you couldn't make that happen. You can't take the bottom of the chain and jack that up to the top. But in practice, that will work and give you the same exact answer. The reality method makes sense, right? You can imagine why everything in that integral is what it is. It all makes sense logically. This is a little bit of a mind stretch. So it's a mystery.
But gravity is the same.
Gravity is the same.
Yes.
Yes, same. So you should do both of them and see that you get the same answer. There's a lot of times that in these physics problems where there is another way that is quicker. Like that's definitely much more work. Your limits are 20 and 40. You've got the extra block. Here you have a limit that's 0, and you're just going up to 20. So let's do it this way, and I'll leave the other way for you to do, because I don't think we'll have time to do both. So let's do one of them. So for our integral here, we're going 0 to 20. The acceleration is 9.8. The density, we said we're just going to have a density of 1. I just made it with 1 so that it was simple. And then the distance traveled, we said, is 40 minus y for each link. And then what is length?
dy.
Just dy. So that'll give us the work done in magically lifting the lower half of the chain. So we'll have 9.8, and when we do the integration, that's what we'll end up with. Plugging in the 0 gives nothing. Plugging in the 20, we'll have 800 minus 400 over 2,
So 600?
600.
What?
800 minus 200?
No, I thought you said y squared, not 200, not 600.
And then what's that? 600 times 9.8. We should be able to do that in our head, but
56.
5880.
5880 joules. So then, one of your tasks should be to show that you get 5880 on the other one too. Questions on any of the work problems that we have just been doing? Or a homework question? We had one homework question that we haven't answered yet. Should we look at that homework question? Yes, let's look at that homework question, because we have 2 minutes, which is plenty of time to do this simple, easy question.
So simple.
Simple and easy, right?
So simple.
Okay, so here we have a triangle. So let's draw a picture of this triangle. That's going to be our base. And that's a terrible triangle because that should be an isosceles. Okay. And the cross sections are parallel to the y-axis and they are semicircles. So you're imagining this element at x and it's going to create a semicircle. So we have this stack, this sideways stack of semicircles. And they're getting smaller and smaller and smaller and smaller until they decrease to a point. Visualizing it? So we've got a semicircle coming out of the board at each place. We use a vertical element because they say we're parallel to the y-axis. The area of a semicircle is determined by its radius. That is the radius of the semicircle. The radius is not the function, right? This function is y equals 16 minus x. Slope -1, y-intercept is 16. So what is the radius?
Minus x squared. No, wait.
1/2 of that. Because the 16 minus x is giving you that whole diameter. Right? That 16 minus x is measuring from the x-axis up to the curve. We want half of that for the radius. And then the area of the semicircle, it's going to be half the area of a circle. So it's 1/2 pi times the radius squared. So that is the area function. And then we integrate the area to get the volume. All right. Today is Wednesday. Have a good weekend. It feels so far away. See you on Monday. If you have questions, you can post them right into this collaborative area and I will answer them. You can use the Ask My Instructor. And I will get back to you.
Test is the 13th?
Test is the day before Valentine's Day.
Oh, great.
Happy Valentine's Day.
Will you show us so much love by giving us 100%?
So much love. Maybe I'll find something to give you. And it will be red.
Emotional support.
Not my test score, hopefully. Have a great weekend.